Hey there, I'm going to do my best to explain what I think is going on in 4510 right now. I'm going to deformalize a lot of the terms and some of the process just because I've found personally that getting bogged down in a lot of the notation is making it a lot harder for me. It just makes me need to reread things. So I'm gonna take it a little less seriously. And honestly, it'll probably just make it harder to understand, but there's nothing you can do about it because I'm here and you are on the other side of your computer screen. So first, I need to talk about Turing machines, what a Turing machine is. That's critical. A Turing machine is just a program. And for our purposes, we'll say it takes in a string and it returns a Boolean. We call that Boolean accept or reject. You could call it true or false, yes or no, doesn't really matter. Of course, it's possible that it doesn't return anything. So it returns a Boolean unless the program doesn't halt, right? It's possible when you're writing a program that for a particular input, the program just never stops running. And if that happens, then you never return true or false, it just doesn't halt. The Church-Turing thesis says that a Turing machine has the same computational power as anything else in the world. If you've come up with some computation engine, some computer, whether it's, actually physically in existence or just theoretical, as long as it's physically realizable, as long as it's possible to build a computer to these specifications, then it doesn't have any more computational power than a Turing machine. Okay, so a Turing machine has the same amount of abilities. It can do the same things, maybe not in the same amount of time, but it can do the same things as any other computational engine that can possibly be built. The way I like to think of it is that a Turing machine has the same computational power as JavaScript. You'll see I'm very, very fond of JavaScript. So then we have to discuss languages. And of course, we've kind of gone over these already in CS 4510, but I want to define it formally because I think it's important. Now, a language is just a set of strings. Normally, instead of being defined by a dictionary, like we do with actual human languages, we define it using some rule. It just takes a lot less space to write it out. So this is set notation. And it just means that the language L is a set of strings where each string only gets to be in the set, that is, in the language, if the string has even length. Now, in this case, we can't write a dictionary of every string in L because there are a lot of those, but it wouldn't be hard to make a machine, maybe a DFA, maybe a JavaScript program, that can figure out whether an input string is in the language. What's important is that a language can exist even if you have no idea how to compute it. For example, I will probably never know what sentences are in this language. Maybe no one can ever know what sentences are in this language. But even if it's literally impossible to make a complete dictionary of strings that are members of the language, or even a program that tells whether a string is in the language itself makes theoretical sense. A language is a set of strings, but there are a lot of things we can represent as strings. A DFA, for example, isn't very hard to turn into a string. Just write out a description of each state and the transitions from one state to another, and then which ones are the accept states. If you come up with a good procedure for that, you can convert a DFA into a string and a string into a DFA. Maybe you'd encode it in a slightly more reasonable way, but this would work, right? And this just shows that if we can have a set that contains strings, we could also have a set that contains just the strings that result in some particular kind of DFA. So we can actually make languages that include DFAs if we just say in reality the language just includes string representations of the DFAs. Okay, this gets a little more hairy, but it's still just a set of strings which can act as representations of DFAs defined by a rule. There are a bunch of different ways to write a DFA that accepts only even-length strings. In fact, there's an infinite amount. And our language L includes every hypothetical DFA that works for this purpose, and excludes every DFA that doesn't work for this purpose. So that's languages. Now we've got to talk about how to build a machine for a language that takes in an input and figures out if that input string is in the language. We've already seen that there are some languages that can be perfectly encoded by a DFA. A DFA will always stop once it finishes reading the input string, reporting yes or no, so for many languages, it's possible to run a particular DFA on that input and just say that the string is in the language if the DFA accepts, and the string's not in the language otherwise. PDAs have a little bit more power. They can do some things that DFAs can't do, but Turing machines, also known as JavaScript programs, are the ultimate power. If your Node.js runtime can't figure out whether an arbitrary string is a member of a language, which is called deciding the language, no one can, not even God, or Zvika Lil. But does this kind of language exist? Is it possible to come up with a language that can't be decided by JavaScript? Surely not, right? This is JavaScript we're talking about. It will surprise you, but even JavaScript is incapable of deciding some languages. These languages do exist, and we'll talk about one in a second, but we have to build up to it. First, realize that just like we managed to make a language that includes some set of DFAs, we can write a language that includes a set of JavaScript programs, aka Turing machines. So like before, we could define this language. To be clear, this isn't the language of strings with even length. This is the language of strings that, when interpreted as JavaScript programs, can tell you whether or not the input string has even length. That JavaScript program has to work for every input string. And by work, I mean it's got to actually return something. Remember that JavaScript programs can return true or false if they terminate, but they could also just not terminate. So this language only includes the JavaScript programs that actually work for this purpose. If you've ever TA'd a class where you have to read students' code, you'll realize that there are many, many, many very creative ways to write such a program, and that's okay. Each hypothetical program that actually works for this function is part of the language. So the general idea is, what if we wrote a JavaScript program that tells whether another JavaScript program is in L? So it's like an auto-grader. It takes in some JavaScript source code as an input. It figures out whether the program does what it's being asked to do, which is tell whether an input string has an even length. If the program does work, it's in L, and if it doesn't, it's not in L. So if you could build a perfect grading program, you would be deciding L. You'd be figuring out which strings, which JavaScript programs, are in the language and which aren't. The grading program has to halt, of course, or it wouldn't be able to decide L because it wouldn't always report an actual grade, and then the student would go complain to the dean of students, and then you would get in trouble. Soon, we'll prove that it's actually impossible to build such a grading program. I'm realizing as I say this that grading computer science homeworks is literally impossible. I need to find a new line of work. Anyway, the Sipser book introduces a solid gadget that we can use to prove a crap ton of things about Turing machines. It comes in the form of a language called A. Look, I'm sure Sipser or whoever named this language is a really smart dude, but A is like the worst possible name for a language. It means nothing. It's not descriptive. I have to go back and look at the definition every time it comes up just to figure out what Sipser's talking about. So I'm going to rename it just like I renamed Turing machines. And again, you cannot stop me because you're on the other side of your computer screen. I'm calling this language English because it fucks everything up and literally no one knows what is or isn't actually a word in the language. So English is the set of tuples. A tuple is just a comma-separated string, right? So it's the set of tuples, j, s, where j is a JavaScript program, and that JavaScript program returns true when you call it on s. So it has to return. It can't not halt, right? It has to terminate, and when it returns, it should return true. English is a super fundamental language that's not decidable. That means you can't write a JavaScript program that does this, that takes in some JavaScript source code and an input string and figures out for sure whether the JavaScript code will return true. If that program did exist, this is what it would output. So decide-English.js takes in a tuple, takes in j and s, and it just tells us whether j and s are a happy tuple. It tells us whether the JavaScript program j returns true when you call it on s. If it does, then that happy tuple is in English, and if not, the tuple is sad and is not in the English language. Now keep in mind, any Turing machine can emulate another Turing machine. There's this cool project written entirely in JavaScript by masochists, Mozilla, that can interpret and evaluate a JavaScript program. Now it seems like deciding English is kind of obvious. If you want to see if J will accept S, you just run J with S as the input and see what it outputs. But what if the code you're running has an infinite loop? What if J loops infinitely when you call it on S? Then your decider will also loop infinitely and you'll never get to return false, which is what you should return because J didn't accept S, it looped forever. So you'd have to do some kind of analysis on the code beforehand to make sure it doesn't loop forever. And it turns out that's hard. Impossible. So let's prove that English is not decidable. Again, that just means that writing decide-English.js and having it always correctly return true or false is actually impossible. Let's suppose the opposite. Suppose decide-English.js exists and it correctly decides English. That is, it'll accept if and only if J accepts S. I'm using red and green here because I know it'll piss off somebody I know who's taking this class who is red-green colorblind. Now we're going to make a new auxiliary JavaScript program called ruineverything.js. And here's the procedure. Ruineverything.js will take in the source code for some JavaScript program as an input. It runs decide-English.js, which is guaranteed to halt because it's a decider, and if it didn't always halt, it wouldn't always output a decision. Remember, the point of decide-English is to figure out whether the program input will accept the string input. In ruineverything.js, the inputs to decide-English, get this, are the input source code as the JavaScript program and the input source code as the input string for that JavaScript program. Then it just outputs the opposite of whatever decide-English.js said. If you need to rewind, I don't blame you. This is crazy shit. So ruineverything.js takes in some code and just returns whether that code fails to accept its own source code as an input, whether that code rejects or fails to halt on its own source code. We were able to build this algorithm only under the assumption that decide-English.js is a real program that actually exists. Since decide-English.js is guaranteed to halt, ruineverything.js is guaranteed to halt. What happens if you run ruineverything.js with its own source code, that is the source code of ruineverything.js, as the input? Take a second, think about it, pause the video, I'll be right here when you get back. You good? You got it? Cool. Crap. Sorry about that. Right, we have a contradiction. Ruineverything.js, when called on itself, will return the opposite of its own output on itself. So that doesn't work. That means that the main component of ruineverything.js, which is decide-English.js, cannot possibly exist, because we've managed to use this gadget to construct a perfectly sensible Turing machine that contradicts itself. So English is undecidable. It is impossible to write a JavaScript program that will always tell you yes or no whether a particular string is in the English language. And remember that the English language is honestly a pretty useful basic thing. We're talking pretty fundamental things about JavaScript programs here. It just lets us know if this program returns true when called on S. It really shouldn't be that hard to figure out programmatically, but it is. So the first interesting corollary of this is the halting problem. The language halt looks like this. Halt is the language of program input tuples, where calling the program with that string as the input will result in the program halting, terminating, ceasing to run. Turns out halt is also undecidable. That is, you can't write a program, will this halt.js, that looks at a program and an input and figures out whether that program will halt for that input, figures out whether j, s is in the language halt. Again, we'll do a proof by contradiction. Assume will this halt.js does exist, and since it's a decider, it always terminates. if we can figure out how to write decide-English.js given just will this halt as a component, then the existence of will this halt implies the existence of decide-English. Remember that decide-English just tells us yes if J will accept S, and no if J will reject S or if J doesn't halt on S. So how do we write decide-English.js with will this halt.js as a component? Easy. Let me write you some pseudocode. Okay, so like always, in decide-English.js, we're given two inputs, a JavaScript program and a string. First, we'll call willthisHalt.js to find out whether J halts on S. If J doesn't halt, return false, because obviously J doesn't accept S if J never even stops running on S. If J does halt, then we just run J on S. We know it'll terminate eventually because willthisHalt told us so, so now we can confidently run J on S without having to worry about our decider failing to terminate, and we can return the right result. So having a program that tells us whether some program J halts on some input S means that we can decide English, which we've shown to be impossible, so it must also be impossible to make a program that tells us whether J halts on S. It turns out you can do a lot of these reductions with just a little bit of work. If you want to show that a language is undecidable, that is, its decider is impossible to implement in JavaScript, just look for a way to write decide-English.js using this other language's decider as a component. If you can do that, then the language must not be decidable because we know that English is undecidable, and having a decider for that language would break logic, and Milena will be very angry if you break logic because we were using that. Take this language. Can we build a decider for this language? Well, let's try to finagle a way to decide English, given that we do have a decider for this language. Call that decider decide-L.js because I'm just not creative anymore. The same idea. Let's write out decide-English.js. So like before, the inputs are some source code and S. Now, given this source code and this input, let's make a new JavaScript program called auxiliary.js. Now, this auxiliary program has an input, which I'm just calling input, and then J and S aren't inputs to the auxiliary program. They're hard-coded in there. You see that? We call J of S, but just kind of assume that all of the source code for J is dumped right there with S kind of already put in as a parameter. Right? We're actually creating this auxiliary.js file as part of running decide-English.js, and then we'll execute it later. So in this auxiliary program, if the input is the string we're looking for, we just return the output of running J on S. Of course, this might not halt, but whatever. If the input isn't the string we're looking for, just return false, reject. Now, run our L decider on this new program. Since L is a decider, it must terminate, and we're assuming that decide-L.js does exist, and that it works. It tells us whether the input program accepts Hairy Grapefruit. The input program accepts Hairy Grapefruit if and only if J accepts S. So this whole program works perfectly to decide whether J accepts S, which is the objective. That's how decide-English.js is supposed to work. Of course, the problem is that English is undecidable, so it must be impossible to come up with a program that decides L. Because of that, we know that L is undecidable. So now, if you can't do question 2 part B on the homework, I'm not sure there's much I can do for you. At the end of the day, I'm just a JavaScript fanboy, and it's okay to hate me for that. It's okay. If you're confused or if I fucked up, drop a comment on Piazza or email me at tja@gatech.edu. Keep in mind, I just learned this stuff too. I'm not totally sure it's right. And I'm a little busy right now, but I'll do my best to help you out if I can.